Hello everyone, April 25th. I woke late today. But the problem to solve, it's an engineering problem, but it's very, very complicated to deal with. Alright, looks to be very simple. I mean, yesterday's problem is actually very simple, but I didn't notice, then it become very bad. Alright, zero index integer array and integer modulo and integer k. Your task is to find the count of subarrays that are interesting. A subarray is interesting if it follows the condition. If count, like count be the number of indices in the range L to R, such that nums I modulo equal to k. Then count modulo equal to modulo. A subarray is interesting if the following conditions holds. Let count be the number of indices such that we have these k, now we have count number that modulo that, and then we want count to also be modulo that. Count of interesting subarrays. Alright, so I have 3, 2, 4. Modulo 2. So mod 2 equal to 1. Right, so mod 2 equal to 1. So who mod 2 equal to 1? Only this one mod 2 equal to 1. Right, this one mod 2 equal to 1. And we need to count, so mod, okay, so basically this, we pick out all the numbers that satisfy, right? So basically we have one number, another number, another number. So we have these numbers, right? Then we also have the count modulo equal to k, right? So we will be able to know what the count is, right? We start from k, right? Start from k, and then k plus modulo. K plus modulo, and then plus modulo, plus modulo, plus modulo. So in this case, 1, I have 1. So basically we're asking, starting from, like, including all these, right? Because these are the minimum. Right, let's say we need, yeah, we need a sum. And then for each subarray, starting from, like we say, we starting from, right, basically we have something, 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 good one. Something, 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 good one. Something, 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 good one, right? If we say we need 2, right? Then we say we need this and this, only including these 2. Oh, we can do this multiplied by this, right? So that's only including these 2. No, not including this one. So it has to be, so we get the indices of these out, right? However many, we just take, like, this will be this multiplied by this. So in this case, only this one's good, so I have 2. So they also can have, we can have 0. Right, so basically to the left plus 1, to the right plus 1, yeah. So next one, basically we have 0, 1, 2, 3. We have 0, 2, and 3. These are satisfying. right? And then k is 0, so our requirement is to have 3. Right? We need to have 3. Oh, count can be 0. There's no index I in the range 1 to 1 that satisfies. Oh, because it's 0. Yeah, so we start from count k. Count k is actually 0, so now you need to find. Ooh, 0. What if it's like 3, 1, 2, 9, 6? Yeah, well, what do we do that? So we want to count 0. Any that does not involve. So basically we have this. I think it's the length, so I just want to know how many. It's n minus 1 times n divided by 2. So this is 2. Oh, oh. Uh-oh. Because we can do n. Alright, we start from here, we have n. So it's n plus 1 times n divided by 2. So in this case it's 3. 1, 2, that's 3. That's 3. 4.
Oh.
Where does 4 come from? How come it's 4? Oh yeah, it is 4. Because you have 3. Yeah, okay. So yeah, we go with k, whatever k is. And if k is 0, then we go through them to find gaps. Right, we'll go through them to find gaps. Oh, but if you do it that way, That is going to take a long time though. Because you start with k. Yeah, k equal to 0, I think I can probably do it as a separate condition. Yeah, because I have these two, and then I just find the gap in between, That can be done separately. I think what I want to figure out is if k is a number, if we have the length, right? When we have the length, we look for front, we look for back, and then we do that. The thing is, we can't just plus this. It is like a sliding window, right? But how many times do we have to do this? Well, k is length divided by k. Actually, no, because we can go from 0 k plus modulo, k plus 2 modulo, right? So O(n) log n, I think. And if it's k equal to 0, it will have a special treatment. Alright, let's try it. So I definitely, the first things I want to do is to get all the numbers out, right? What do we call this? We call this find all the numbers that modulo equal to k. Then we use sliding window to find all the subarray of length k plus p times modulo, where p equal to 0, 1, 2. To find all the put them in a vector. Of the vector of length. Yeah. And we say from each subarray we can compute the total number of interesting subarrays. K equal to 0 is a special case. All right, so we call it good. All right, and then for int, I need indices. If nums I, okay, modulo equal to k. That's a good dot pushback. Ooh, I can push back I directly. That'll make computation easier. All right. Now what we need to do is long rest equal to 0. If k is equal to 0, then we do something, right? Once we're done, k plus equal to modulo. That's the first one that we will handle. Okay. Now we have a k. Okay. Then basically what we need is while k is smaller or equal to nums dot size, right? K is the size. Then we have low and high. Right? Or actually we don't need low and high. We just move forward. Right? We just move forward. So basically what we have is for I plus k. If k is 1, then the length is 1, which is just by itself. K is 2, so you plus 2. So that should be something smaller or equal to k, smaller or equal to a good. Right, I plus k is the size. Right, if k is 2, I plus I is 0, 0 plus 2 is 2. So the size shall be 2, and the size should be smaller or equal to the good size, right? So for each one, I can find j. Okay, so int. Actually, I think it would be easier if we just call it low and high. Right? That's high. So this is the two indices. One pointed to low, one pointed to high. Then what do? Well, we will go to the good array. And from the good array, we'll find the indices. And from the indices, we can compute. Right? We can compute. I do believe it may be easier to... Hold on, let me think. It may be easier if I have something else. Like if I starting from an index and I find its previous index, right? Let's say I am looking at 3 and my previous is 2. Okay. If that's the case, then that's 3 minus 2 minus 1. Because we want to know, actually no, it's just 3 minus 2. Right, just 3 minus 2. Just this minus the previous one. And if the previous one is not 2 but 0, then you actually have 1, 2, 3, right? You have those. So, and for the future is the same. So I think it will actually make things easier. If I do this, good.pushback, -1, blah, blah, blah. Once it's done, good.pushback, nums.size, right? So now when we do this, the low will start from 1, right? And then basically this shall smaller than good dot size minus 1, right? So we have extra at the front and extra at the end. Okay. Now we have a low and a high. We can say rest or plus equal to. Well, I need to long this thing. Long good. Low minus good. Low minus 1 multiplied by good high plus 1. why are you hesitating? Just high plus 1 and multiplied by good, not multiplied, minus good high. Right, so that's the total number on the left hand side, on the right hand side. Oh. So yeah, that's that. And then I think once it's done, oh, that's just the one round, right? K. So we're done. K plus equal to modulo, right? We increase by modulo, and we try it again. Yeah, each time we'll include different. Okay, and then once this one's done, then we can return rest. All right, now we just need to handle this. So k equal to 0. What we need to do is go through them, and each one we will find a number, like the length in between. Yeah. Okay. For int I equal to 1, smaller good enough size, I plus plus. All right. What do we do? Long. Okay. What's this? Size, count. Right? Shall be good. I minus good. I minus 1. Right? 0, 1, and then minus 1. This one already done, so this multiplied by count plus 1 divided by 2, right? Because you 1 plus 2 plus 3 all the way to plus 2n. All right. Okay. All right, let's give this a shot. Let's see. This feels like significantly longer than the solution I took a glimpse earlier. All right. Let's see if we can hit just the first shot. Ooh, TLE. Damn. Okay, we TLE. TLE. Why would I be TLE? Because this is all the same. Oh jeez. Modulo 1 mod 1 equal to 0. Oh, that's just everything. Huh. That's just everything. Yeah, the good just everything. So there's no saving there. And k will be plus equal 1 every single time. There's also no saving there. Can we say like starting from because it has to be exact count, right? Can I find each size in like O1? Because right now we have to go through another sliding window. Right, for this length, I need to go through the sliding window. Basically this times this, and I will move to next. And now I say this times this, and next this times this. So basically we have some values, right? And we have these are the gaps, right? And what we do is like if it's this 2, then we do this times this, and then move on to the next one, this times this, next one, this times this, right? Any patterning there? Well, the pattern is if I do like I say I'll pick this, okay, and then I say I'll have this, and next time I'll have the other one. So basically this is going to be G1 times G3, right? And if we extend again, so maybe like actually no, this is that's G1, G2, G3, G4, right? And the next one, let's say that's this. Next one can be A1 to A6, right? And then that will be G1 times G7, all right? And then we have the next one. So basically, yeah, based on what this one is, well, plus current. Yeah, plus K. And then K, oh no. Plus modulo. We have the starting one, and then we'll plus modulo. Plus modulo, we have many modulo, and then they all be like this, right? So in this case, G1 times G3, because I do this, right? G1 times G3, the next one should be A4, so actually A5. So basically it's G1 times like G, 1 plus 1 is from K, right? And this is from modulo M plus G1 plus 2M plus G1 plus whatever M, right? In this case, M is equal to 2, because that's the length. Oh. So this is gonna be G3 plus G5 plus all the way to G, something M plus 1, right? Can we get this fast? And it'll be the same, because the next one will be G2, right? G2 will start from G5, right? So this is the exact same thing. We don't have to recompute it. That seems to me a prefix sum, a suffix sum, essentially, right? A suffix sum. Nah, not really. We add this together. Okay, we add this together. This will be used for the first one, right? We add this together, and each time we move forward, we just remove this, remove this, remove this. Okay, that makes sense. So we just need the gap for the first one. Right, the first gap is always 1, and we need to find the sum of all the gaps. Right, the sum of all the gaps. The gap, what is the gap? Do we include or not include? Well, I think it's including. Right, it's include. The gap includes. Yeah, it's just minus. Yeah, we just do a minus. And then we will find the total sum of these minuses. So we find gap 1 is always going to be that, and then plus modulo is just we find the index. So in this case, m equal to 2, right? And we find gap 3 which is 1 times, and what is gap 3? That's actually not gap 3. That technically, I think that's gap 2. Gap between 2 to 3. Right? And we use gap 3 to represent, but it's between 2 and 3. Between 2 and 3, and it's going to be minus 1 minus that. So that's that one. And then once we're done, we move it forward until we can. So we add everybody together, right? We add everybody together, and then we use the gap 1, okay, multiply by that, and then my number move forward, right? I just move on to the next one. So I move on to the next one. So that means we need to remove a gap, right? What do you mean by remove a gap? Because at G1 I gap to G3, right? And if I move forward, wait, hold on, let me think again. So it's the first one, the gap 1, and then it lands here, so I have another gap, right? And then they will, which is to add this, add this, add this, or add everybody. Now I move forward. Huh. It got shifted. Yeah, this doesn't work. It got shifted. Yeah, because everybody shifted to the right a little bit. How? Man, it's another. It feels like it's gonna fail again. Yeah, if you move forward, then you're actually taking the next gap, the next gap, the next gap, the next gap. Oh, there might be a way. Hold on, hold on, hold on. What we're looking for is the number of sizes, right? Size k plus modulo. How many different ways k plus modulo is? No. No. I have too many hints. Prefix sum. Okay, I did not consider prefix sum in this case. Prefix sum. Let me think. Total number of subarrays. We can say ending at this. Okay. No idea. Yeah, let's just check his solution. I think it was pretty hard last time too, because look at this. We were not able to solve it. Let count I be the number of indices where among the first count I be the number of indices where nums I among the first I indices, okay? Count I. Yes, okay, yeah. So count, right? I have each position is the count, how many in the past and the previous satisfies. Okay, that's fine. Calculate for each how many indices j is smaller than I such that how many indices. Okay, so basically I have a count I is the number to the previous, and a count j is, yeah, we just need to find the count I minus count j is the in between modulo equal to k, right? So I have count I, right? I have count I, and count I minus count j modulo this equals k. So that each means count I minus count j need equal to k, right? Equal to k, k plus modulo times 2. Then doesn't that just mean, because I have count I is here, right? I want to know how many j, but how many count j? Because count j is a value, right? Count j is value. So from count I, okay, from count I know what count j need to be, right? I know what count j need to be, because if modulo, if I know modulo, which is going to be k, then count j is going to be count I minus k, right? Count I minus k, and then count I minus k, that number, right? That number, we want to know how many indices to the left. So there could be a counter, right? We can have a counter for the value, right? For the value. So we check count I minus k. We see how many have that. Then we do that, okay? And then we do modulo, plus modulo, plus modulo, plus modulo. So the worst case, right? The worst case is still O(n) squared. Right, because each one you have to, for each count I, we can have many different. Actually, no. We can save the value, right? I think we can save the value, because I have right now count I is small. So if I look back, I can only do k. That's it. We find the k, we get whatever it is, right? So the next one we can do k minus k again. Next one we minus k again. And at a certain point, I can do minus k, and I can do minus, k minus modulo, right? And but still, I don't. Let's keep reading. I don't know. Like it's still O n squared. Rewriting this, count I minus count j. Count j will equal to count I plus modulo minus k. Yeah, that's right. But hold a second. Oh, you don't have to count j. And then we use a counter for this. Sum up all the map. Modulo. So hold on, let me wrap my head one more time. So we're at count I, all right? And we can do, count I minus k, count I minus k minus modulo, count I minus k minus 2 modulo, right? And count, they all become count j, right? They all become count j, which means count j, if I modulo it, it's equal to count I minus k, well, plus modulo, right? And then we modulo. So everyone that satisfies will have the same modulo. I think I know what it is. Okay, so in other words, when we record the number, right? We don't record the number. We record the number minus k plus modulo. That's exactly, I think, what is said here. We record this. But wait, no, we don't record this. This is what we trying to find. When we record, we just need to record modulo, right? Like why do we just record modulo? Because when we do this, right? We do this. That's the number. That's the key we want to find, which means each number when we add, we need to we need to know what its key is. And the key is going to be, hold on, let me think one more time. So this is the last step. I don't understand this one. Why we modulo it with a current? current count? Well, we modulo it because we have the current count, right? And we need to find the current count minus k. Okay, current count minus k. We have something. Current count minus k minus 2 minus modulo. We have something. We have something. Okay. But they all share the same characteristics, which is if they modulo, they all become current minus k plus modulo and modulo, right? They all share that same characteristics. So I need to put them as this characteristics, right? That's what I need to put them as this current characteristics. But to put it at this characteristics, then why we just modulo it? Yeah, that part I don't understand. Why do we modulo it? Why do we modulo it? When we do the count. Doesn't make any sense. Right? We have the current count, and we need to know previously, because I have all the previous counts, right? So I want to know how many count is this, how many count is this, how many count is this. But all those counts have the characteristics, right? The characteristics of those count is if I take their modulo, the modulo are the same. That's why you need to do the modulo, because the characteristics is their modulo is the same. Okay, I'm convinced. Yeah, this is not easy at all. Pretty darn hard. Hint. Have to use the entire 9 hints and a lot of additional thinking, right, to convince myself. The tutorial, the hints are pretty good. Briefly, right, we want to use a prefix sum to find to keep track number of elements that modulo equal to k. Right, that's what we want. And then to find all the subarrays, all the interesting subarrays ending at nums I, right? We check count I, right? Then find j such that count I minus count j, right, count I minus count j modulo equal to k. Right, that's the goal in minus count j modulo. This means count j shall equal to count I minus k minus p times modulo. Or in other words, yeah, where p equal to 0, 1, 2, 3. Notice that regardless of p value, of the value of p, all count j has the same, all count j have the same modulo remainder when count j render as count j minus k plus modulo. Modulo. Right, they all have this characteristics. Such count I, count j. Let's count I. In other words, we the number of subarrays. Interesting. Subarrays ending at I is the same as the count of right. This is a count of this. Yeah. We can use a counter to keep track of that. So I don't even need this. All I need is a unordered map called a counter, right? And starting from every number, I will try. So basically 4 for every number that get out. I need to see what is the number that before it, right? Ending at current, right? Ending at current. So we need to find is the count. Good count, right? So good count is the current, so we do good count minus k plus modulo, right? That's the good count. after we get the current one. Right? Now we have a good count, go to counter, we try to return it, and it will be like 0 or whatever, doesn't matter. And then we keep going, and each time we go, we'll keep a record of at this position was the mod, right? What is the value so far? So I can just say this, right? And I need to get a good count first. Right? That's essentially what it is. And mod modulo equal to k. Right? If it is, then we include the good count. And then we will say res. Say res are equal to long, res plus long counter good count minus k plus modulo mod modulo, right? Once we're done, counter good count mod modulo plus equal to 1. We can just say plus plus, right? It's just the good count so far, and then I move on. Oh, come together right now. Ugh. Zero. Yeah. So the first count now is 1. Count is 1. Yeah, it has to be 0, right? We don't have 0, so currently. Oh, we do have 0. Because 0 is always a good count. What's count 0? It just means because that's a counter as a frequency, right? This just basically means when you have 0. Good count is 0. And good count is 0. Yeah, we need that. We need that. Yeah. Oh, I mean, that's okay. We did a lot of the reading of the hints. Wow. I've been having a very bad streak lately. Mainly, it's, you do it kind of late, and that definitely is not helping. I was trying. I couldn't figure out. Finding the number of subarrays whose sum also equal to k. Yes. Not necessarily k, it could be multiple of k. A sum's modulo. Right, sum's modulo. So we have a prefix sum, and we need to do that minus something. Then result is good. Right, then we just need to know how many in the past has a value that's good for us, and in order to eliminate repeated, we use another round of modulo. Yeah, I think that makes more sense now. I think it's pretty darn hard. All right, that'll be it. Tough question, I think. I'll see you guys.